I hope you can hear me well. I see thumbs up. Okay, thanks. So you can hear me? Yeah, so I guess you noticed or you got the email that unfortunately we cannot have the lecture all today, and that's why I'm giving this lecture from my office. Um, and just to remind you that last time we talked about file systems and specifically about NTFS as one example of a file system. And basically, we went through the main data structures in NTFS and let's see, um, and looked at some core concepts. And most importantly, we looked at file operations. So, which data is stored in the master file table, which data is retained when you delete a file, and stuff like that. So topics were the master file table as the main data structure, how that looks like, where you have basically one entry for each file. We talked about addresses. Okay, we talked about attributes. So in the MFT, for each entry, we have a header, and then we have the attributes, and each attribute, once again, has a header and a body. And yeah, we looked at some examples for attributes. The probably most complex one was the data attribute, or in practice, the typically most complex one was probably the data attribute, because you often have the data not within the MFT, because the files are too big, but they have to be stored on another position on the hard disk. So we have to define the cluster runs, and we had a closer look at cluster runs or data runs, to be more precise, run lists. So a number of runs stored consecutively, and we had a look at that data structure and looked at an example, which is also a common task for the exam, where of course we would supply you with that slide here, or the contents of that slide, if you had to do that in practice. Okay, what else did we talk about? We briefly mentioned the metadata files of NTFS, and finally there's operations like creation and deletion of files, and some extra features like encryption or compression and alternate data streams. So that was the main content from last time. Were there any open questions? I believe I missed one question that I was sent by email, as I remember now. So I asked one of you to send me an email with one of the questions, and actually forgot to have a look at that. Sorry for that. And yep, I will reward the person who sent me the email with chocolate when we meet in person again. Okay, if there are no open questions so far, I guess we can continue with the next chapter. I'll just have a brief look at the chat. But no comments there. Okay, then let's skip to the next lecture. Oh, okay, I see someone started the meeting earlier and ended it in. Okay, anyway. So let's continue with the next chapter. So far we talked about persistent data, and now we will switch to ephemeral data. So data that is lost when you switch the system off. And okay, that's the wrong chapter. That is the right chapter. So this time we're going to talk about ephemeral data. So typically the main memory content and that is data that is lost when you switch the system off, as mentioned before. Now, the goals of the chapter are that you know what types of ephemeral data there are. I mean, there's a large number, but we will look at some 4 categories. We will have a look at how to decide whether we should try to access ephemeral data and perform live forensics. And we will briefly mention some tools, though, as usual, the main part of the tools discussion is going to take place in the tutorial. So this chapter deals with ephemeral data collection, or we could also say it deals with live forensics, because live forensics is performed on systems that are still running, so systems where you can access that ephemeral data. So live forensics might also go a bit further, because of course you need live forensics to preserve ephemeral data, because you cannot do that after shutting the system down. But while you are at it, of course, you can also connect some additional information, either because you're doing the live forensics process anyway, and it doesn't hurt to get some extra data quickly, or because you perhaps don't even plan to do a post-mortem analysis. So imagine you suspect that your company has fallen victim to a ransomware attack, and say 500 computers might be affected by that attack, and you are afraid that those computers might start encrypting their hard drives, and you want to investigate who caused that. But you might not be certain yet. So you will not want to shut down 500 systems and do a full analysis of the hard drives and perhaps perform a full duplication of all these hard drives if you're not even certain what happened, or if you're not certain how many computers were affected. So maybe you can just do a quick check on all these computers, and maybe you find out that only 2 were affected. So you might only want to do the full analysis on these 2 computers. So live forensics goes beyond just what you need to preserve ephemeral data, but also helps you decide how to continue. Anyway, what you always need for live forensics is access to a running system. So if the system is shut down, you cannot access the system. That seems quite obvious. Now, let me first ask you a question before we continue. What kind of data would you expect to find in main memory that should be preserved, or what other kinds? Maybe some stuff is in main memory but doesn't need to be preserved. So what can you think of? What data would you find on a running computer that might be worth being preserved? Any comments? Feel free to speak up or to type something to the chat. RAM contents, yep. And what kind of contents would you expect in the RAM that might be interesting for an analysis? Password hashes? Yep, true. Cache data? Yeah. Are you thinking of any type of specific caches? Process tree, correct, sure. Call stack. So a lot of information about running programs. Processor caches. Processor caches are a bit hard to access directly. I mean, you can find out what information is cached, but it's not a simple process. So I wouldn't expect the processor cache to be normally used in a forensic investigation, but it's a good idea. File tree, yeah, might be. So if you don't want to do full forensic duplication, just looking at what files are stored on the computer, maybe evaluating that later on. Yeah, sounds plausible. Anything open ports? Yeah, and that's a good point. So looking at network-related data, anything else about the network or network-related data that might be interesting? Or maybe I ask a question about the open ports. What are open ports? Network traffic? Yeah. So you could try to preserve the entire network traffic, or yeah, look at specific data like visited websites. Mm-hmm. I mean, to some extent, that might also be in the persistent data, but it doesn't hurt to look at the browser history during live investigation, assuming you take care not to alter data while doing so. Let me get back to the open ports. What does it even mean? Okay, so I guess that's an answer to my question. Depends on what one wants to achieve. For example, in case of malicious software, might want to look for connections to known servers. Yep, looking for connections that are ongoing, which may be established through ports. Yeah, in the end, yes. So, but what's the meaning of an open port? Okay, maybe we'll have a look at the following slides, and I have those topics on the slides as well, so maybe that will be the right point to discuss what those specific aspects mean in detail. But yeah, let's get back to that later. Now, still, that's a lot of interesting information, but on the other hand, doing live forensics is usually risky. So whenever you install software or even run any program on a computer that alters data, firstly, potentially on the hard disk. So there might be some log files that are written that say something about the process being run. And of course, installing a program or running a program, running a process will change the content of the main memory. So might destroy evidence used by doing live forensics, or you might disrupt the business. If you're doing live forensics on an important server, the server might not be available for the usual tasks. You might want to stop connections while doing so. Or the fact that you're running forensic tools might alert an attacker if there is actually an ongoing attack performed by a human, which is definitely the exception, but it might happen. And software, forensic software might even cause system crashes. So that's unlikely, but not impossible, especially if the software is not run on exactly the correct system. So it might be tailored to a certain system configuration. And if you run it on a different system configuration, it might cause a crash. On the other hand, a regular shutdown might also cause changes and potentially even more changes than just doing the forensic investigation. And the third option, of course, between shutdown and doing live forensics is just shutting off the power. But that might leave persistent data in an inconsistent state or corrupted state. So that's also not an ideal choice. Of course, you have to do something. So basically what you do is you choose the course of action that causes the least damage, though any action will cause some damage. So anything you do could cause a change. Not doing might lead to the loss of data, because of course processes are still running. Even if you didn't execute them, there are still running processes. Other people might access the server, so evidence might be lost anyway. So it's always a weighing of different factors to decide whether you perform live forensics. These factors could be following factors, might be others. So first of all, if there is critical information that is not present elsewhere, then it makes sense to perform live forensics, definitely. And we talked about the most common case for that, that would be an encryption key. So if you have an encrypted hard drive, the system is running. As soon as you shut the system down or cut the power, the encryption key is lost, and then you might have lost all access to the target system. Secondly, do you have the right circumstances to run live forensics to minimize changes to the target system? We'll get back to factors influencing that point later, but at its core, it means, do you have experience with live forensics on that specific type of system, operating system, and system configuration? Do you have the right tools to do that? Is the environment suitable? So do you have time for doing live forensics? Is it a mission critical run system? Stuff like that. Thirdly, I mentioned the example beforehand. Do you have a large number of affected systems? You might not be able to do offline forensics on 500 computers. So doing a quick check, doing live forensics might be a reasonable way. Related to that, if forensic duplication would take an excessive amount of time or would even potentially fail, then doing live forensics might also make sense. By excessive amount of time, I mean, of course, a large amount of storage of hard drives, of systems, or large hard drives, and large number of them. And that means you might not be able to do the forensic duplication, or it might fail, for example, due to encrypted systems. And finally, there might be legal considerations. What data are you allowed to investigate? Are you allowed to do a full offline investigation, or maybe the client or whoever wants the forensic investigation to be done wants to sit next to you for maybe half an hour and check what you're doing, but might not want to allow you to take the entire hard drive. So these are important factors for the decision. And of course, always one has to take into account the integrity of the evidence that you preserve. We will want to minimize risks when doing live forensics. So I mentioned beforehand, you should have experience, ideally. So if you have done the live forensics process, if you have knowledge about the tools that you can use on that system, that's definitely helpful. So ideally, you should have tested live response process on a similar system beforehand and maybe have some experience. You might want to consider performance issues. So if it's an online shop server and the entire company will go bankrupt if the server fails, slightly exaggerating, then yeah, it's an issue that you have to take into account, because running forensic tools might degrade the performance. For the same reason, you should think about potential system crashes. And there is the nice acronym of CYA. So you should have communicated with the stakeholders. So the people who have a say in the system, so the manager of that online shop system, for example, should have given approval, ideally written approval, or at least some documented approval. That might also be an email that might be prudent in such a case. And I guess you know what the acronym CYA means. Okay, any questions or comments so far? If you're wondering if we will get back to the question I asked, we will. We're not getting to the point where we first look at how to access the data, and then we're going to look at what data might even be covered. Now, the first problem in many cases might be how to access the systems. If you want to investigate your own system, or you have been tasked by a client to investigate their system, you will normally not have an issue with accessing the system. You will know usernames and passwords. But otherwise, well, say it's in a system which is currently either in standby mode or the screen is locked, then it might get challenging to access the system for live forensics, because you cannot just reboot the system, obviously, because you want to have access to a running system. Now, what could you do? You could try a brute force attack, hoping for a bad password. That might be problematic. There are some systems around that will automatically shut down or wipe memory contents if the wrong password is entered too often. Not very common on desktop computers or even laptops, more common on other mobile devices, but still something to take into account. Other than that, of course, brute forcing passwords might take a very long time and might also fill log files, for example, with entries about unsuccessful entry attempts. So in the worst case, that will cause other data to be overwritten. So it's something that I would want to avoid. Now, there are two well-known attacks which can help you access main memory if a system is still running without having to brute force passwords. And they are called DMA attacks. Okay. But over FireWire is actually mostly outdated, but DMA attacks still exist, so just forget the last two words here. And cold boot attacks. So has anyone of you ever heard of either of the two attacks? I would hope so, because I mentioned them in the first lecture, I believe. Only about cold. Yeah, true. I only mentioned cold boot attacks. Anyone know what a DMA attack is? Or what DMA is? So DMA stands for direct memory access. And basically it means a mechanism that allows direct access of any connected devices, any periphery of the computer, without having to go via the CPU. So you can directly access main memory contents without causing additional CPU load, which obviously makes sense for performance reasons. So basically you allow some connected external graphics adapter or what else do you typically connect, USB flash drive or whatever, to access main memory while mostly bypassing the operating system and the CPU. Therefore, per se, we will learn about a mechanism that helps with that, but per se, the access control of the operating system doesn't have an effect. So originally, that meant for systems susceptible to a DMA attack, that you could just plug in something via a FireWire, or nowadays Thunderbolt or USB-C, and automatically directly access the main memory content. So that means you can basically read the entire RAM content using an external device without being stopped by any access control mechanism. So obviously, that is not a good idea to allow that access. So of course, there have been some modifications. So many years ago, a component was introduced called the Input-Output Memory Management Unit. So basically a hardware component that manages access to memory from external devices. But of course, the IOMMU does not know on its own which parts of memory can be accessed by external devices and which ones cannot. So, say, for example, the USB flash drive is supposed to copy some of its content to main memory, or the GPU, the external graphics adapter, needs to read some data from the main memory. Then, of course, that should still be possible. But what area of the main memory can be read has to be decided somehow by the operating system. So obviously, an IOMMU only makes sense if the operating system uses it. So without support by the operating system, an IOMMU is useless. Now, a couple of years ago, a study was published in NDSS, which is one of the most prestigious security conferences. And it revealed that the IOMMU was not used at all by some operating systems, and other operating systems they investigated were able to use the IOMMU, but were not by default configured to do so. So actually, though the mechanism had been around for a couple of years, even then, the operating systems didn't use them. So it wasn't possible, quite trivially, to access main memory content from external devices that you could just plug in. And yeah, that allowed you to copy all the data, including encryption keys, without many issues. So that is obviously a bad thing for security. Basically, the risk of open USB ports or Thunderbolt ports had been known for a while even then. So corporate policies of some companies basically did not allow the use of these ports. So they were disabled in default configurations. But overall, that's the exception. So most computers used operating systems in their default settings and did not have any protections against the DMA attacks. So until 2019, it was very common to be able to do that DMA attack. macOS, by the way, was an exception in the later versions. Now, even nowadays, following that publication, some changes were made, so it's not as easy anymore. But even in that publication, it was already pointed out, and that hasn't really changed much since then, that there are attack vectors that allow to circumvent that protection. And the main issue that you have in practice, and that's the thing that did not change or improve that much in recent years, is device drivers. So device drivers supplied by the manufacturers of these external components, they are usually not really optimized for security, but for cost, development cost on the one hand, and performance on the other hand, and they can be quite complex. So you will often find security issues, so classical software vulnerabilities in these device drivers, and that still allows, in many cases, to do the DMA attack. So basically, you attach an external device. The device driver is either already installed in the system or might also be automatically installed when you plug in the external device. And then you exploit some security vulnerability in the device drivers, which are very common to occur. And those will allow you to get access to the system. So that means that in practice, the DMA attack is now only possible if you have experience and you know the tools to exploit these vulnerabilities. So you will normally have specialized forensic investigators who know how to handle those tools and keep themselves updated about common vulnerabilities that they can exploit. But it's not such a big issue to be able to achieve or to perform a DMA attempt. Though, as I said, some changes were made by the manufacturers. So nowadays, I believe all the operating systems will use the IOMMU at least. So the security standard has been increased following the publication, as it usually happens after such a study is published. But the main issue here still remains. So, any questions or comments so far? Or maybe one more comment from my side. Of course, if you exploit such a security vulnerability and perhaps you're using the wrong version or make a mistake during that, then there is a risk that the system crashes. So that's one more case when a live forensic investigation is not without risk. And why you should have some experience before trying that in a real case. Okay. What else? Originally, as I said, it was done using FireWire. Here I've listed some traditional tools for performing a DMA attack. Now, the next attack I want to mention is cold boot. And once again, the idea is to circumvent the operating system when accessing RAM content. And this time, there are basically two versions. One is you do a reset of the system and boot a different operating system. So you try to read data from the main memory that is preserved while you reboot, or you remove the entire RAM modules and read the content from the RAM modules. Now, the issue of especially the latter, but to some extent also the former version, is that RAM needs to be refreshed periodically, at least DRAM, which is still the most common RAM, and it needs to be refreshed every couple of milliseconds to maintain the information. So the basic assumption is that data will get lost if you power down the system or if you remove the RAM modules from the system. However, there are different goals. So under normal circumstances, you want to make absolutely sure that not a single bit is lost from the main memory. So to achieve that, you need to refresh every couple of milliseconds. But if you can live with a certain probability that some bits change, then you might be able to live with longer refresh periods, and that might allow you to still read some contents at least a couple of seconds after removing the RAM module from power. Under some circumstances, that can even be minutes. And the circumstances that I mean mostly mean that you have to cool down the memory modules. So you use cooling spray to cool down the memory modules to something like -30, -40, -50 degrees. And that slows down the decay of data, and it gives you a couple of extra seconds, or in extreme cases, even minutes, after removing the modules from power, and you might still be able to read most of the data. There is still a risk that bit errors will occur, but you might be able to live with that. Now, as I just mentioned, we can perform a reboot and copy the memory content shortly after the reboot. And secondly, we could cool down the memory modules, plug them into another machine. For the first version, basically, you would boot from a USB flash drive and then do the memory dump. And for the second option, you need to remove the memory modules. Now, I briefly showed you a list of challenges of cold boot attacks, but maybe if you haven't really looked through that yet, you might try to come up with some ideas of your own why that might be challenging. Sorry, I was a bit too fast with showing this slide, but I guess you didn't really have time to look at it. So let's start with the first version. So with the booting from a USB flash drive, what might happen that prevents you from doing that? Why could a cold boot attack be unsuccessful if you do the cold reboot and then try to read the memory contents afterwards? Can you always boot from a USB flash drive? Yep. So USB ports might be deactivated. So if you don't have a working USB port, then you cannot boot from USB. You might then try to change the system configuration in the computer setup BIOS or whatever. But in that case, yeah, you cannot. So if you cannot reconfigure the system, then you cannot boot from the USB flash drive. Exactly. Or what else might happen? If you have no access to the BIOS, yeah, okay. So if you have access to the BIOS, you might change the configuration. Otherwise, many systems are configured by default to enable boot from a USB drive. So it's quite likely that it will work, that you can boot from the USB drive. Some systems are actually configured to wipe the memory contents when you reboot. So in that case, of course, the cold boot attack using the USB drive will not work. And even under the best of circumstances, you will not be able to read all the data from the main memory. Why not? What happens if you boot an operating system? The operating system might override parts of the memory. Of course, operating system is also a computer program that is executed, like computer programs that are executed within the main memory. So, of course, some of the memory content will definitely be overwritten when you reboot. That's why you always try to use a minimal system that basically only has enough capabilities to copy memory content. So you will not normally lose a lot of data for that reason, but you might lose some of the data from main memory. It will not normally be a practical issue because most of the application data will not be stored in the first couple of kilobytes of the main memory. But that's definitely a good point. Now for the second version. Why might that be challenging? Cooling down the memory modules, removing them, plugging them into another machine. No idea? I'm working on my laptop right now. Do you think the Coltwood hack work? The RAM might be soldered to the board. Yes, that is quite common on mobile devices nowadays. So yeah, exactly. So that is a common challenge. Not so much on desktop computers, but on any kind of mobile devices, including laptops. At least some of the main memory, the RAM modules, might be soldered onto the board. So removing them might be extremely challenging. I have listed some more challenges on the next slide. One is, okay, there are multiple RAM sticks that all need to be rammed. Yep. But if you can remove them easily, that's not such a big issue because they can still be powered. You can remove them while they are still powered, so you can just read one after the other. You only have to make sure to store the image in the right order, but that should be doable. Now, a challenge that has made it more difficult over time is increasing storage density and reduced voltages mean that the memory contents decay faster than they used to. So in the original paper on Coltwood Attacks, which was some, I think 15, maybe 18 years ago, they really managed to preserve data in some cases for a couple of minutes. That is no longer doable right now, at least from my experience when we tried this at my chair. So the times were a lot shorter in recent years with current memory technology. Right. Reboot of USB sticks may be prevented by the system configuration or might be overwritten. We mentioned that before. We mentioned RAM modules being soldered onto the mainboard. That does not prevent the reboot, of course, from the USB stick, but it prevents removal of modules. And finally, a challenge is, no, more challenges are that the very crucial data might be protected. So keys might be stored in CPU registers. That's one countermeasure against Coltwood attacks. Or memory encryption might prevent you from reading the main memory content. And even if you have found if you have been able to dump the memory content, identifying encryption keys might also be a challenge. Do you have any questions so far about Coltwood attacks or their challenges? Because for the next couple of slides, we're going to go into detail about the last aspect, how to identify and potentially correct encryption keys. So we mentioned before that Coltwood attacks might give you most of the data, but it's quite common that some data is actually lost. So you might have flipping bits, and usually it's only in one direction. So say ones are turned into zeros because of the decay of the memory contents. So yeah, you have some way to identify and reconstruct encryption keys, but that might not always be trivial. By the way, I don't have that on the slides, I believe, but how would you try to find encryption keys in the first place? So the next couple of slides will explain how to make sure that you found an encryption key and maybe also how to correct the encryption key. But yeah, do you know any properties that might make it easier to find encryption keys? Well, encryption keys for symmetric encryption schemes will normally look like random data. So you can look at the entropy of data, And say if you find larger areas with all zeros or all ones, then it's most likely not an encryption key. And they have a fixed size, yeah, usually. Okay. Now let's do some, give you some background on one way of identifying or making sure that you found an encryption key. So you could look for some entropy regions in main memory and then make sure that you found an encryption key. Or you might have found an encryption key, but there might be some bits in there and you can reconstruct the original encryption. Now, let me give you some background. And most commonly for symmetric encryption, we use AES, like 128, 192, or 256 bits. And AES has an interesting structure that might make it easier for us to find encryption keys using redundancy. So we have an original key, master key. We'll take the example of AES 128 here. And for AES 128, we have the key that we would normally refer to as the AES key, the master key. But for each round of AES, we will derive a round key from that master key. So we have different round keys, and for performance reasons, most implementations, or probably all major implementations of AES, store not just the 128 bits of the master key, but they will store all the round keys, and the combination of all round keys is referred to as the key schedule. And because the key schedule has a structure, we can we have redundancies in the key schedule, and we might be able to construct missing round keys or the missing master key or altered master key. And additionally, it enables us to decide whether we even have an AES. So the structure of AES 192 and 256 is mostly the same. There are some more complications for the key schedule generation. So we are doing the simpler version here because it's only about illustrating the principle. So basically what we have is we have the plain text, and in the first round we do some operations with the round key and the plain text, and the result is some intermediate state, and we continue that for a number of rounds. In AES 128 it's 11 rounds. And in the end, the result is the ciphertext. Now, the rounds are not all identical, so the last round, as you see here, is simplified, and the others here do some slightly more complex operations. But we are now mostly interested in how the round keys are derived, because that's what we find in the main memory. We find the master key and all the individual round keys, usually consecutively stored in memory, and that's the structure that we will use. Now, a key schedule looks like that for AES 128. Each round key consists of 16 bytes. Well, you could have computed that yourself, because 16 bytes is 128 bits, so that's the length of the master key and also each round. So yeah, 0, 1, 2, 3, and so on, and it continues here for the other rounds. Overall, we have 176 bytes in this key schedule for AES 128. Round key 1 is identical to the master key, so that's what you would normally refer to as the AES key that we use for encryption. And the remaining round keys are derived from that. So from the master key, or more precisely, basically each round key is derived from the previous round key. Now, the derivation rule in the case of AES 128, we have a complex and a simple derivation rule. Here we have the round key of round I, and that's the following round, round I plus 1. And for the first byte, what we do is we take a section of the previous round key, do a rotation operation, we do a substitution based on lookup table, the SBox, and then we XOR that with a round constant, which is defined in the AES standard, and we XOR that result with the another section of the previous round key to derive the new round key. And the simple derivation is just doing an XOR of one section of the previous round key with the previous section of the new round key. So that's a simple XOR operation. So overall, we do these XORs for the following bytes. And yeah, that's the way that the key schedule is derived. You don't need to know that in detail, but the interesting thing is that we have a deterministic derivation of the key schedule. So if we have part of the key schedule, that allows us to derive the remainder of the key schedule. Even if we have some bit errors, that structure will help us to correct these errors. So an algorithm by itself works, or maybe I should start at the beginning. So if we have a key with bit errors, then what we want is we have the key schedule with the errors, and we want an algorithm that outputs candidates which are compatible according to a given error model. So that means the candidates that we output might be valid key schedules that were altered by the errors introduced during the cold boot attack. And the error model, as mentioned, will usually be something like we expect all bits only to flip from 1 to 0, but not from 0 to 1. Because the probability that bit flips in one direction happen is usually a lot bigger than for the other direction, because it's about lost charges. So what we store in the memory are electric charges, and they will not magically appear from nowhere, but they might only get lost. So there is an algorithm by itself which basically assumes that 16 bytes determine the entire key schedule. And it's not just that you could use the first 16 bytes, the master key, but there are many other positions. So search paths where you could start looking or assuming that these 16 bytes are correct and determine the other values from that. So choosing some of these 16 bytes already implies the values for other bytes. So you compare the bytes that you guessed and that are implied, and you can compare that with the memory dump. So basically, you do a plausibility check whether your current candidate is compatible with the memory dump according to the error model, and you backtrack the search if the certain assumptions that you made are wrong. So basically, if you see the candidate is not compatible with the error model, you go back to a previous step. We're not going to go through the algorithm in detail. The important thing is that knowing some of the bytes will allow us to reconstruct the remaining bytes of the entire key schedule to be correct. is the basic principle clear of basically how AES works? So we don't need the mathematics to determine why AES works, or why that's a good algorithm. But basically the goal is to show you that there are redundancies, that we have the key schedule, and the principle of how we could exploit these redundancies to correct bit errors in a memory dump. Any questions? Okay, so in practice, some information about creating a bootable USB drive, but that's more for for trying that yourself. So let's get back from this excursion into AES to our main topics. What do we actually do with the data, and what data might we collect? And that goes back to the question that I asked earlier. So we store the main memory content, which contains all of the other information, but it might be much more convenient to evaluate our results if we also collect some more data separately, like the clipboard content. So many systems will have the concept of something like a clipboard, where you copy some images or text to paste it somewhere else. So that is something that can easily be preserved. Also, what I call ephemeral file systems. Of course, the file system itself will be persistent data, but a mounted encrypted file system where the key is in main memory, that might be something that you might also copy entirely during a live forensic investigation, or you just preserve the key. That's basically up to you. Also, temporarily mounted file system like network shares, that might also make sense because you would have access to the network shares via the system under investigation, but you might lose that access when you reboot the system. Now about networks, network interface details. Network interface details, by that I mean basically network cards or network adapters. Let me just, we have some noise in the background. I will try to shut that off. Okay. Now, back to the lecture. Network interface details. So for each network card, like a Wi-Fi card or wired Ethernet adapter, note down the IP and MAC addresses. Does everyone know? I guess you all know what an IP address is. Does everyone know what a MAC address is? Okay, that's a stupid question, actually. How can you answer that? What is a MAC address? That's a more clever question, I guess.
It's used to identify hardware or the physical address.
Exactly. So it stands for medium access control. So for media access control, sometimes use singular, sometimes use plural. So medium or media access control address, I think you're right, it's media access control most commonly. Anyway, so it's about access to the medium, so say in Ethernet, each network adapter has a MAC address, a physical address, which traditionally remained constant over the life of the network card or the network adapter. Nowadays, it can also be changed, but in corporate networks, you will usually still have static MAC addresses. So they identify the network adapter, the hardware basically. They also contain some information that might in some cases be helpful in an investigation. So what information does the hardware address give you? Maybe that was too abstract. So if I give you the MAC address that my Ethernet adapter in that computer here uses, manufacturer, exactly. So the manufacturer is or is encoded, or to put it the other way around, MAC address ranges are assigned to different vendors. So that might give you information, or it will give you information usually about the vendor. Now the MAC address can be changed, but most people just retain the original MAC address of the hardware. So that would give you the manufacturer, which in some cases might give you some clues that might be useful. What else? The routing table. What's the routing table? Oh, routing table depending on your dialect. Address of next hop. Yep. Basically for each potential IP address that you want to send an IP packet to, it tells you where to send them. So which is the next hop on my path to that specific IP address range. For many systems, that will simply be for anything outside the internal network, use the following gateway router, and that's it. But it might be more complex. For example, if you have virtual machines running on a certain host system, the routing tables might be interesting, or if you're looking at the router, of course, then the routing table might also contain relevant information. The ARP cache. Oops, where do we have it? What's an ARP cache? Or what's ARP? But ARP is the address resolution protocol. So when you have an IP address, you want to send an IP packet to a certain address within the local network, you need to find the corresponding MAC address, and the ARP cache is basically a cache for these mappings. So it tells you for a couple of IP addresses, or for all IP addresses of which your system knows the corresponding MAC address, it will tell you that mapping. Now, why might that be interesting? ARP spoofing format in the middle text. So yes, a system might give you a wrong answer, or might even send an answer without having seen the question for a certain mapping. So absolutely, yeah, that would be ARP spoofing. Or it might be even simpler. If you want to know with which other computers your computer has communicated, for example, to see how malware has spread through the corporate network, then the ARP cache will give you that information, because it will usually only contain information if there has been actual communication. Now, the detailed behavior might differ by systems. So some systems might, I'm not actually sure how common that is, but some systems might also record answers sent to other computers, but it's not very likely in most networks that you will actually see the information. So in most cases, if the data is contained in the ARP cache, that means that there has been a communication with that specific other computer. So for that reason, it might be relevant. Now, network connections. We mentioned that before. Some of you mentioned that when we... Oh, no, I missed the DNS cache. Sorry. Let's start with the DNS cache first. What is the DNS cache? So DNS is the domain name system. So that's for mapping between domain names, among others. It's a couple of tasks, but one of the main tasks is to map domain names to IP addresses. And that also gives you information what communication has taken place. And DNS caches are really quite relevant. Within the corporate network, you might have a DNS cache on your own computer. So that way you see with which domains your computer has communicated. But you can also look at DNS caches within the network. So a corporate network or your ISP's network will have DNS cache servers that you are going to ask first. So you're not going to do this whole recursive or iterative lookup for DNS entry. But first of all, you will ask your ISPs or your corporate networks DNS server, which will give you the information about cached entries, so what other computers in your network have asked for. And looking there might also reveal something about, for example, botnet communication. So if there is a known botnet command and control server, then finding that server in your DNS cache might indicate that you have a botnet infection somewhere within the corporate network. So that's why DNS caches are relevant. Now, network connections, that was mentioned by some of you when I asked earlier where you could find information. So basically, your computer is currently talking to a specific other computer. Or to, more precisely, to a specific application on a different computer. Now, how do open ports relate to that? What is an open port?
50 यूरो रह गए हैं, तो अब मैं इतने ही आपको दे सकती हूँ, मेरे पास और नहीं है। तो फिर अंकल कहते हैं कि मैंने कहा अंकल, कहते नहीं लेकिन हमने तो आने से पहले 100 पे बात करी थी ना। मैंने कहा अंकल वो खत्म हो गए और इसलिए मैं आपको बैंक ट्रांसफर कर दूँगी। कहते नहीं, बैंक ट्रांसफर नहीं लेता, मैं कैश लेता हूँ। तो फिर उसके बाद उन्होंने मेरे को बहुत सख्ताई से बोला कि तू चाबी और पैसे वहाँ पे छोड़ दे। मैंने कहा हाँ जी अंकल, ठीक है, ऐसे करके।
What is a port in the communication context?
हेलो, हाँ हाँ, नहीं, मैं आपको ये चीज कहना चाहती हूँ कि उस बात को आप...
So I'm referring to TCP or UDP ports. Mapping of network connection to an application. Yeah, I wouldn't have said connection, but you're basically right. Yeah, network endpoint is not that precise. So the network endpoint could also be an IP address. So an IP address is the address of a host or a system, while a port or port number is the address of a certain application on your computer, which might be static, that we're going to get back to that with the open port, or for a new connection, so a client will typically choose a more or less random port number. And open port basically just means that an application is listening to, so tell the operating system, I would like to open a port. That means if a UDP or TCP segment arrives with that port number, please the operating system forward that to me application so and so, like the Nginx web server will tell the operating system if any TCP segments arrive directed to port number 443, the operating system send this TCP segment onto me. I want to receive the data stream. So an open port means that communication is expected, as someone mentioned in the chat right now. So it means the application is running on the system, is expecting communication. And that might be relevant because you might either know that this application is running beforehand, or you might not. If you don't know and the application is still running on the system, that might be a bad sign. So it might be an indication of malware intention, for example. Or it might be an indication of misconfiguration. So maybe you have an application that is listening on a port awaiting communication, and that might be unexpected for you. Okay, network shares then means that you are either sharing some of your resources, like parts of directories in the file system, or maybe attached printers also connected to your own computer, or you might use network shares from other computers. And that might also be relevant information. Any questions or comments so far?
Yes, I know.
Okay, then let's continue. Other data would be system configuration, like any sort of what might that be? Installed drivers, stuff like that. Environment variables that set, for example, search paths within the file system. Kernel statistics, depending on the specific operating system, they might, for example, log the amount of network traffic also. Any logging and monitoring data, either locally or remotely, like if you have set up a separate log server, then of course looking at that makes sense. The current system time and date, including the time zone, that's of course very important if you want to match the information found on one system with other systems, because the clock might be off. So not everyone uses time synchronization using NTP, or the time zone might be set incorrectly, and that is definitely important to take into account. Next, any running code, like any processes which are open, any current process IDs, how long have they been running, any open files or open handles to, say, drivers or stuff like that. So any files that are currently opened by the operating system. The association between network connections and processes. So the network connections, we mentioned those before, but you would like to know, of course, to which application each network connection belongs, and therefore to which process. Any currently loaded drivers for any hardware attached to the system, or modules that allow you to access any peripherals. The users currently logged in might be interesting. Maybe there's a test user logged in who isn't supposed to have access to the system, stuff like that. Next, we get to less ephemeral data. That's what I mentioned before, that sometimes the data might not be ephemeral, but while we're at it, while we're doing lab forensic investigation, it still makes sense to collect the data because it's easily accessible, and it might help you decide options for the next step for the post-mortem analysis. Like which operating system is installed, how much memory do you have, how many hard drives, how big are they, any mounted file systems, stuff like that. Also the installed software, the installed software that automatically starts booting, for example, a web server, database server, malware, whatever. And cron jobs, or more generically, any tasks that are scheduled to run at certain times or time intervals. For the users, listing the local user accounts, group membership. So for some access control models, you can tie access rights to user accounts, individual users, or to groups like the group of admins or the group of staff belonging to a certain project. The login history, when did each user last log in, from which location, so was it a local, was it a local login, or was it done remotely? and if done remotely, from where? For how long was the user logged in?
शायद लड़का हुआ है
Stuff like that.
उसके बाद
System log data. Most operating systems keep a system log about any events like loading drivers and user logins, stuff like that.
मेल कैसे चेक कर ली किस चीज का मेल
Application log data, for example, web browser history or antivirus software log files. And someone mentioned that before when I asked the question, a file system listing, including timestamps for the entire file system might be useful if you're not doing, or if you don't know whether you're doing a full post-mortem analysis later on. Now, any questions about the data that we usually collect in a live forensic investigation? Maybe I missed something as well. So if you have any other ideas, just let me know.
तुमको पार्टी मिलनी चाहिए क्योंकि तुम्हारी वजह से मैं जा पाई हूँ अरे प्यारा तो भाई तुम्हें मिलनी प्यारा है
If not, I guess we have
पार्टी तो मिलनी चाहिए
already finished most of the chapter. We still have some ground to cover, and half of the slides, but less than half of the content, definitely. The first thing is how to collect data, doing so manually or using some toolkit or some bash script that you wrote for that. Automated collection is favorable because you are less likely to miss something. It decreases the risk that you make a mistake. So assuming the script is correct, it will always run correctly and consistently. And it will work faster than you typing some commands into the command line. Finally, if you do individual search, like if you adapt your methods each time, it might help an attacker to find out what you're suspecting, what you're interested in. That's not usually that important because most cases are not an active attacker really being logged onto the system right now and observing you. But in these rare cases, the automated collection will give the attacker less information about your approach. A manual collection, of course, might be necessary if you don't have the appropriate bash scripts or tools. They might not exist for your specific type of system. Or you might not have access to them because you are in a rush. So for that reason, it might play a role in practice as well. To do so, what I'm saying here is mostly common sense. Before doing a dangerous procedure, life-threatening in our case, but it might cause you to lose information. It makes sense to be well prepared, to have practiced what you're doing on a test system. And to know how long that takes. And you should also be aware of some common problems like USB ports are not working, so you have no way to get your automated tool onto the target system, or network adapters are not working, the screen is locked, stuff like that. As usual for forensics processes, documentation is important. Document what you did, when you did it, and include the time zone and the difference between the actual time and system time, once again, to be able to match timestamps later on. To minimize impact on the target system, it's often recommended to avoid too big or complex tools, so the presence of a graphical user interface might be an indication for that. We should have a log at all times, including cryptographic checksums like hash values that you compute during the collection, not later on because it's much less useful later on. So you basically immediately ensure consistency and authenticity, integrity of the data that you've collected. And once again, you try to minimize what you collect in which order depends on the volatility. So how likely is the data to change? We had the differentiation between ephemeral and less ephemeral data previously. So the ephemeral data is the data that actually is likely to change, and the less ephemeral data is just collected during live forensics. And yeah, you should of course start with the more ephemeral data. What else? Like current network connections. Network connections can be severed any second, so that is important to do quickly. Other things like loaded drivers are not very likely to change that quickly, so that might give you an indication for the treat data as evidence. Of course, we keep the chain of custody and document everything. We said that before. Being cautious means you should not interact with any suspect system without having a plan beforehand, and most importantly, be able to execute the plan quickly, because any more time of interaction means more the potential for changing things. Also, say you plug in a USB flash drive and want to use that to get your forensic tool onto the target system, and you think that the target system is compromised or might be compromised, then of course anything that happens to that USB stick might be an attack. So the attacker might alter any data on the USB flash drive, and for that reason consider all files or media connected to the system, including anything that you introduced yourself, to be lost to the attacker if the system might be compromised. Also, credentials like login data to your cloud storage that you entered on the target system are also be considered as compromised. So make sure the attacker, for example, cannot alter your cloud storage account and change the password later on or use one-time credentials for that. Any modifications, of course, are to be avoided, and installing software is a modification, so that should also be avoided. And the suspect system, if you think it might be compromised, there are two reasons not to perform the analysis. Firstly, the system might be compromised, so your tools might also be compromised. And secondly, anything you do in the target system might change the system. So that's another reason to just collect data and then analyze that on a separate system. Okay. Any questions or comments so far? So for automated collection, you can write some scripts yourself. You can buy commercial products, or you can use open source products, of course other free products depending on the type of incident. As usual, any tools that we use should be accepted within the forensics community. It should be for the correct operating system, so no sense in using a Linux tool and a Windows system, quite obviously. Types of the collected data, so for memory images you will use a different tool than to collect network information. How long do the tools take? How easily can you configure them, or how much configuration options do you even have? And what is the output data format? So how can your analysis tools handle the output data format used by the collection tool? Next issue, how to get your tools onto the suspect system. I mentioned before that you will often use a USB flash drive to do that, and you can also use that to get the collected data out of the suspect system, but USB flash drive might not be feasible, for example, because the system does not have a USB port. The system might have a CD or DVD drive, getting less and less common nowadays, but they do still exist. You can use a network share or cloud storage in the end, depending on the type of share. You could have different protocols to to access these network shares, and the credentials for those should be one-time use only or should be changed afterwards. Or you might use streaming tools to stream over the network, but the effect is basically the same. And in both cases, you take care of the credentials. Any questions or comments?
लेकिन मैं जब किसी को ट्रीट करती हूँ मैं चाहती हूँ वो
Just to
बंदा
mention
मुझे वैसे
quickly,
ही ट्रीट
one
करे। मैं
common.
प्यार से करती हूँ बात।
Oh, that's the next slide.
लेकिन
Sorry.
मुझे
Sorry, I
अरे
was
तुम्हारा गला खराब हो गया
on a
दवाई
different
तो यार यहाँ पे मैं वो हो जाती हूँ
Uh,
परेशान।
for
हंसने
Windows,
की बात है मुझे ऐसा
once
लगता है
again,
तुम्हारा दवाई
basically
खा
the same
सकते हो
options that
ये है मेरा
we
तरीका
mentioned in general
तुम्हारा
before.
या तुम्हारा तो तब
Um,
ये मेरे से
and
नहीं
now
होता है
let's
मेरे
decide
मुंह
that
से
then
रोना आ जाता है
जा
जब
रहा हूँ, छोड़ के खुश रहो।
wanted to quickly mention
कम्युनिकेशन इज
Mandiant Redline is a common commercial but
छोड़ने की
free for
बात नहीं
personal
है
use
छोड़ना नहीं
मैं
tool
छोड़ रहा हूँ, मैं से नहीं होता
that
खुश।
contains
तेरे साथ नहीं होगा
yeah,
तेरे से किसी के
tools
साथ
for what
वही
we
तो नहीं
discussed
होगा, मैं
before,
कैसे कर दी।
collect the data that we mentioned before.
और हमारी इस
Um,
चीज पे बहुत बार
there
बात
is
होती
a
है तो
collector
शोभित से प्यार
tool
से बात करा करो शोभित
without a
वैसे
GUI,
यहाँ नहीं आई वो काम करने के लिए
basically batch scripts
मैं वो भी कर चुका
मैं
हूँ, छोड़
अभी
to
दिया।
be
आपको
run
अपनी
on the suspect
सहयोगियां बना
system
सकती हूँ मेरे दिल
हजार
में
में
हो
and
तो मेरे को
a
प्यार
GUI
से
tool
बोलोगे
for a separate analysis
बस
system.
ये कमी
But we
रह
will
जाती
not
है
go into
मेरे
detail, I
पेरेंट्स भी
mean the
मेरे से प्यार
screenshot
से
for
नहीं
that,
करते
but
अरे तेरी सेहत बहुत
as I
बहुत है
said, the
तू
practical
तो अरे
considerations and
यार
use of tools, not just Mandiant Redline, but other tools,
आपके
is
ना
mostly
तुम्हारी
for the
बनानी पड़ेगी
tutorial.
बनानी
If you
पड़ेगी
want
मैं
to
जितना आटा की
develop
बनता उतनी
tools
बना लो, मैं
yourself,
तुम्हें हाँ,
think of
जितना बनता बना लो,
operating
मैं
system
तो कुछ कहता
versions,
नहीं, मेरी एक तो बना दो,
32-bit,
दो बना दो, तुम मुझसे
slowly
बाद में
dying
बोलोगे
out, but
मैंने
still
दो बनाई
existing
थी तुम्हारी
versus
रोटी, मेरे को
64-bit.
सुनना नहीं, सुन जितनी मर्जी बना
Um,
दो।
ये तो मैंने कभी नहीं
ओए
and
रॉन्ग
मैं
in
अपनी
your toolkit
रिस्पॉन्सिबिलिटी पूरी
collect
करती हूँ
कल
all
बोल
the
रही थी
tools that you
तुम्हारे
need,
जाने से पहले मैंने 2 रोटी
including
बनाई।
जाने से पहले मैंने ये कहा था कि
built-in
मेरे को
commands
तुम्हारी फिक्र है
from the
2
operating
रोटी
system.
फिक्र होती है तो बोलते नहीं
Now,
है, फिक्र
the
होती है तो
next
बोलते नहीं
slides
है।
are a couple of
मैं 5:30 बजे
examples
उठाता है,
for
खाना बनाया,
built-in
मैंने एक
tools
बार भी नहीं बोला कि मैं
for
शायद तुम्हारे वहाँ
Windows,
छोड़ने भी गया था आके।
but we will not
मैं
have the time because
मैं
we
वो
only have 3
बोलता नहीं
minutes
हूँ, मैं
left
बोला नहीं
for
था।
today.
उसको पार्टी दे
मैं पार्टी से क्या करूँ, मुझे कुछ भी नहीं
तो
चाहिए,
हमारे पास वही है देने के लिए और कुछ नहीं
मेरे को चाहिए नहीं, मुझे सेक्स चाहिए,
To
सेक्स दो।
today.
पागल।
अगर अपने लिए तुमने देना ही था तुमने भी खानी है तो आटा ज्यादा क्यों
So basically,
मेरे को भाई तुमसे ज़्यादा काम नहीं
we
कराना, मुझे छोड़
check
दिया,
the
मैं टोटल
calendar. I believe next week
अपने अपने ईगो ईगो से ही चलो
क्या ईगो?
we do
तुम्हें काम नहीं करना देना
have
चाहता था, इसलिए छोड़ दिया।
the lecture
मैं कहाँ
back.
काम कर रही हूँ मैं तो अपने लिए रोटी बना रही हूँ
Or
क्योंकि
is
मुझे
it
भूख
public
लग रही है वो
holiday?
तुम दे
No,
सकते
next
हो
week is
बना
a
के नहीं
public
दे सकते
holiday,
ना
if I'm not
तो मुझे ही
mistaken.
बनानी पड़ेगी
So we
मेरे
will
पैसे
meet
बनते नहीं
again
हैं।
in the usual lecture hall on the
कह रही मैं
25th, which
तुम्हें
is
काम
going to
नहीं
be
करने
in
देना
2
चाहता पर
weeks.
करूँगी ना मैं रोटी
वो रोटी वाला
Um,
छोड़
तीनों
दिया,
टाइम
मेरा नहीं देना चाहता, इसलिए छोड़ दिया।
that's fine.
हाँ
Yeah,
अपना कर
next
दो
week
तुम्हें दिख रहा है
is
कि
a public
ये मैं तो
holiday.
अपना
Please
खा ही रहा हूँ
contradict me if I'm wrong.
वो तो एक बनती है सेंस
And if I'm not wrong,
कि हाँ यार ये
then
अपना
I
बना
will
रही है मैं इसको
probably
साथ में
just
अपना भी कह दूँ
stop
बनाने
sharing my screen. Maybe as a final side note, not
ये चीज बहुत
directly
मेरे को
related to
कमी
the
लग रही है और ये
lecture,
चीज मैं
my
खत्म कर दूंगी
background
बिकॉज
image
ऑल
is
द
from
टाइम
the
आई डोंट
University
लाइक
of
दैट आई एम
Edinburgh,
कमिंग टू यू कि
which is
सब्जी बना दो
connected to
सब्जी
the
बना दो
history of
सब्जी बना दो
forensics
सब्जी बना दो
because
आई विल फिनिश
Joseph
इट आई विल
Bell,
कुक फॉर माय
who
सेल्फ
was
फिनिश
sort of a role model for
खाओ
the
बनाओ
Sherlock
अपना खाओ
Holmes
बनाओ
stories,
मुझे तुम्हारे सामने
he
हाथ
worked
जोड़ने
at that
पड़ते हैं
university.
सब्जी बना दो अब अगर सब्जी ना हुई
And
तुमने
if
नहीं
you're
बनानी
interested in
थी
the history of
तुमने बोल
forensics,
दिया था मैं
you
1
might
बजे
want to read
बनाऊंगा
about him. Um,
तुमने नहीं बनानी थी
and or visit the University of Edinburgh, which is a very nice place.
रखो यार
Other than
अपने
that,
लैपटॉप के पास
please
रखो
have a nice
मुझे
day
नहीं चाहिए
and
प्रोग्राम के लिए
see you
करनी
in 2
वो
weeks.
काफी है उससे
Bye
ज्यादा
bye.
मुझे कुछ नहीं चाहिए ना पढ़ाई में चाहिए ना वो वीजे में चाहिए ना किसी चीज में चाहिए दुनिया के और लड़के लड़कियां मर नहीं गए वो मर नहीं गए हैं तुम नहीं अगर हेल्प करोगे मैं किसी और के पास चली जाऊंगी
ओए क्या वो
कुर्सियां तो बहुत ज्यादा सुंदर लग रही हैं ऐसे कमरा तो मैंने नहीं देखा आज तक
खत्म, टेंशन गई खत्म, अब चलो मैं फ्री हूँ।